Hi everyone, welcome to our first video for week 2. This week we're talking about probability, which is going to help us connect that descriptive statistics discussion from last week to the rest of the course where we're talking about inferential statistics, making predictions and verifying results. I'm going to apologize, I probably sound a little funny today. I've been sick over the weekend, so I am sorry for that. Please bear with me. Let's start with some new vocabulary. I'm going to go through this pretty quickly. Probability experiment is any experiment that is governed by chance, so a chance process, that leads to well-defined results, meaning we know the possible events that are going to happen when we roll that dice or we flip that coin. Well-defined results. An outcome is the result of a single trial of a probability experiment. So a single roll of the dice or a single flip of the coin. The sample space is the set of all possible outcomes of a probability experiment. If I'm flipping a coin, my sample space is heads and tails. So for example, let our probability experiment be rolling a fair six-sided die. Fair is important because that lets us know that each of those outcomes has the same chance of occurring. The outcome for this probability experiment would be the side of the die that faces up after one roll, and the sample space are the 6 sides of the die, the 6 possible sides that could face up. So our sample space is 1, 2, 3, 4, 5, 6, and a single outcome could be any one of those numbers. Probability is the likelihood of an outcome occurring. That's the definition we learned last week. Or the long-term relative frequency of that outcome. Meaning we can figure out probability by repeating a probability experiment over and over and over and over and over, and then looking at that relative frequency for the repeated trials. When we say outcomes are equally likely, what we're saying is that each outcome of the experiment has the same probability of occurring. For example, if we flip a fair coin, I expect that I've got a 50% chance of getting heads and a 50% chance of getting tails. We would say that those outcomes, heads and tails, are equally likely. An event is any combination of outcomes. So we know an outcome is the result of a single run of the probability experiment. An event is any combination of possible outcomes. So let's go back to our dice example from the last slide. Here are some possible events when we roll a die. We could roll a 1. That's a single outcome. We would call this a simple event. One single outcome. Rolling a 3 or a 4, this event is multiple outcomes, 3 or 4. We would call this a compound event. Rolling an even number would also be a compound event. The even numbers in our sample space are 2, 4, and 6. So this event is made up of 3 outcomes. So that is a compound event. We're going to talk today, or rather in this video, about the probability for simple events, and then in later videos we're going to introduce how to address these compound events. So let's talk about probability rules. First, any individual probability, so the probability for any single event or outcome, will always be between 0 and 1 inclusive. So the smallest probability we can get is 0 or 0%, and the largest is 1 or 100%. If we sum up all the probabilities for each outcome in the sample space, the result should be 1 or 100%. So back to our dice example, if I roll a single die and I add up the probability of rolling each of those sides, 1 through 6, that should add to 1 or 100%. If the probability of an event X equals 1, that tells us X is going to happen every time we perform the experiment. That is a guaranteed outcome. I know it's going to happen. If the probability of X occurring is equal to 0, that tells me that event X will never happen. Not possible, cannot happen. An example of P of X equal to 1 would be if we're playing with a standard deck of playing cards, we know all the cards in the deck are red or black. So the probability of drawing a red or black card would be 1. That's going to happen every time I draw a card from the deck. If I'm using that same deck of standard playing cards, the probability of drawing a green card is 0 because there are only red and black cards in the deck. So let's look at how we calculate probability. Classical probability uses the sample space to determine probability, meaning we're using what we know about the system to figure out how likely an outcome is. For classical probability, we are assuming that all of the outcomes in the sample space are equally likely. In symbol notation, the probability of event E happening is the number of outcomes that are in E divided by the number of outcomes that are in S. E being the event that we're interested in, and S being our sample space. In words, the probability of event E happening is the number of outcomes in our event E divided by the number of outcomes in our sample space. If we go back to that dice example, we talked about rolling an even number being a possible event. Well, we know that even numbers are 2, 4, and 6, so the number of outcomes in E, even numbers, is 3. The total number of outcomes in our sample space are the 6 sides of the die. So NS would be 6. So the probability of rolling an even number for a fair 6-sided die would be 3 over 6. And I forgot I did that on this slide. A note here, you'll notice that I have a fraction answer and that I have not reduced it. You will notice with probability that we don't reduce our fractions because it makes it easier to see connections between probabilities and compare them. You do have 3 options. You can leave it as an unreduced fraction, or convert it to a decimal, or you can convert that decimal to a percent. You're going to see me use these 2 forms, fraction or decimal. And as we get further in this probability unit, you're going to notice that I lean more heavily on decimals as the preferred form. Empirical probability, on the other hand, is based on actual data. So empirical probability uses a frequency table to determine probability. In this case, the outcomes may not be equally likely. We don't have to make assumptions in this case because we have actual data. In this case, the probability of an event E happening is equal to the frequency for event E divided by the total frequency of the frequency table. So frequency for the class divided by total frequency. This should look familiar because this is also our definition for relative frequency. So empirical probability is just a relative frequency. So we've got an example table down here of 3 methods of transportation. And we're going to use this travel survey data below to find the probability that a person will travel by train or bus over the Thanksgiving holiday. So we're looking for train or bus. We're going to go down to this frequency table and find that class, train or bus, and pick off that frequency F. So train or bus has a frequency of 3, so the top of our fraction is going to be 3. And the total frequency in the table is 50. We surveyed 50 people. So P train or bus is going to be 3 over 50, or 0.06. So as the number of repetitions of an experiment increases, the empirical probability obtained approaches the theoretical probability. So what we see happen in the real world should approach what we know about the system's behavior in the long run. We're going to use an example of a coin toss because we know that theoretical probability off the top of our head, 50% heads, 50% tails. So let's look at a coin toss simulation. So what this website does is it models tossing a fair two-sided coin, and it's checking the probability of a heads occurring. And it's assuming for any single toss that 50% heads, 50% tails. So we're going to start with 15 tosses, and then we're going to slowly increase that number and see what happens to that probability of getting a heads in the long run. So we can see over those first 15 runs, we got 6 heads and 9 tails. So that blue line is slowly approaching 0.5, hasn't quite got there yet. So let's add some trials to our run. Let's go 25. So it performed another 25 trials, and we can see now 19 out of 40 and 21 out of 40, getting closer to 0.5. Let's try another 25. Not quite 50-50. We're at 31 out of 65 and 34 out of 65. But you can see this blue curve is slowly flattening out and getting closer and closer to that 0.5 expected value. Let's try this a couple more times and see what happens. So right now our probability of heads is 0.489. Let's do another 25. And 0.478. Let's try a whole lot more. Let's do 200 tosses. So we've done a total of 315, and you can see we're at 0.464, not quite at that 0.5. We try it again. We're getting closer, 0.482. And we can watch this blue line kind of slowly creep closer and closer and closer to 0.5. So after 715 trials, we're at 0.489. I'm going to link this applet on Canvas. I keep wanting to say Google Classroom, sorry. So you guys can play with it on your own. I would encourage you playing with it and also adjusting the likelihood of getting a heads and seeing what that does to the test. But let's go ahead and go back to our presentation here. So we saw the word or earlier in our presentation, so we're going to look really quickly at or versus and. When we say or, we're saying that the outcome is an A or B, or both. So in this picture, I can see that the red are the outcomes in A, the blue are the outcomes in B, and this overlap that looks kind of purple is the outcomes that are in both. And everything that's shaded in this picture is A or B. A and B means the outcome has to be both A and B. So looking at a similar picture, the A and B is just that purple region. And when we say A and B, we're limited to that overlap. So or B is more inclusive. It can be both, or it can be just one. A and B means it has to be both. So let's do an example. We're going to let A equal 1, 2, 3, 4, 5, and B equal 4, 5, 6, 7, 8. And you can see that I have drawn a picture that kind of outlines what those two events look like. We can see that 1, 2, and 3 are just in A, 6, 7, 8 are just in B, and 4 and 5 are in both. So only in A is 1, 2, and 3, only in B is 6, 7, 8, and in both is 4 and 5. So A or B is everything in this picture. 1, 2, 3, 4, 5, 6, 7, 8. A and B is only the stuff in the overlap, 4 and 5. We're going to use this when we start talking about compound events later this week. Note in A or B that we didn't double count the 4 and 5. It only shows up once. So we don't want to double count events or outcomes. There's only one 4 and one 5 in this sample space, so they should only show up once when we're looking at A or B. Okay, really quick, more vocab. Complements. A complement of an event is all of the outcomes that are not that event. So simple example, if we're flipping a coin and I'm looking at heads, the complement of heads is everything that's not a head, which would be tails. We write that with a little prime. Sometimes you'll also see it written with a line above the letter, but this book I think uses the prime notation. So complement of A is equal to A prime. And if I add those probabilities together, probability of A plus the probability of the complement of A, that should add up to 1. Because everything that's A and everything that's not A should be everything in the sample space. That does mean that I can find the probability of the complement by doing 1 minus the probability of A, and I can find the probability of A by doing 1 minus the complement. This can be really helpful for compound events when finding one of these is difficult, but finding the other is easy. So we can use this complement rule to find the probability we're interested in by finding the probability that's easier first. Conditional probability is the probability of a second outcome happening given you know what happened first. So we see conditional probability when we're doing multiple things, drawing 2 cards from a deck, pulling 2 marbles from a jar. And the conditional probability is the probability of the second event, assuming we know what happened first. We write it using that slash PA/B, and that's read as probability of A given B. To calculate that conditional probability, we divide the probability of both A and B happening divided by the probability of B happening. And notice it's the given part, given B, that's on the bottom of that fraction. That's important. So we're going to do a quick example and then we'll call this video done. I know it's running long and I'm sorry. The table below describes the distribution of a random sample S of 100 individuals organized by gender and whether they are right or left-handed. And again, books are a little closed-minded. We're just going to run with it. First thing we're going to do, fill in those totals. I need to know how many people I surveyed. I need to know how many men, how many women, how many lefties, how many righties. And we're going to find 6 probabilities. So we're going to start with the probability that a randomly selected person is a man. So the number of men in my survey is 52. The number of people I surveyed is 100. So PM should be 52 over 100. Same thing for the probability of drawing a female, randomly selected woman from that sample. 48 women were interviewed. 100 people total were interviewed. So the probability of randomly selecting a woman is 48 over 100. Similar idea for right-handed. 87 righties, 100 total. PR is 87 over 100. For lefties, we have 13 lefties, 100 people, 13 out of 100. Now let's look at those ands. So PM and R means the person is both a man and is right-handed. That's one box in our table. Where is the M and R box? So that M and R box is right here, male, right-handed. So M and R is 43 per people out of that 100 people. So that's 43 out of 100. Similar idea for F and L. Women who are left-handed, that's one box in the table. There were 4 women lefties in our sample out of 100 total people. Let's go back and try a couple more. So M or F. So I'm looking for males or females out of a total of 100. So 52 plus 48, that's 100. So the probability that I select a man or a woman out of this sample is 100%, or 1, because that's everybody in my sample. Now let's look at M or R. So M or R, I'm looking for the male left hand, the male right hand, and the female right hand. Everybody in the male, everybody in the right hand, and I don't want to double count that overlap. So 43 plus 9 plus 44 is 96, and 96 over 100 is the probability that the person is a male or is right-handed. Repeating for female or left-handed, we have 44 right-handed females. We have 9 left-handed males and 4 females who are left-handed. So all of the females, all of the left-handers, don't double count that overlap. So we add those together. 44 plus 9 plus 4 is 57. So the probability of drawing a female or a left-handed person is 57 over 100. Okay, now some tricky ones. I didn't mean to go forward, but that's fine. So the probability of M prime. Remember when we see M prime, that's the complement. That's everybody who's not male. And we can use the complement trick. If I want the probability of not male, that should be 1 minus the probability of getting a male. So 1 minus 52 over 100 should be 48 over 100. And that makes sense because we can see from our table that you're either male or female. So the complement to male should be female, which is 48 over 100. Okay, next one is a conditional probability. What is the likelihood of selecting a right-handed person given their male? And we're going to use that formula. We know that a conditional probability is the probability that it's both divided by that probability of the given, PM. So R and M is 43 out of 100, and PM is 52 out of 100. So the probability given you're right-handed, or the probability you are right-handed given that you're male, is equal to 43 over 100 divided by 52 over 100, which is just 43 out of 52. If we do the same thing, probability that you're female, given that I know you're left-handed, that would be the probability that you are female and left-handed divided by the probability that you're left-handed. So female and left-handed, that's that 4 box, so 4 out of 100. Probability that you're left-handed is total number of lefties, 13 over 100. So F given L should be 4 over 100 divided by 13 over 100, which is just 4 over 13. Okay, that was a lot of information. We're going to spend the next few videos parsing that into small bits and going over it in more detail. If you have any questions, please let me know. You can reach me via email or text message. Contact info is on Canvas, or I will be having office hours on Tuesday from noon to 1 and 7 to 8 p.m.